So this is the second second part of the temperature measurement. So we stopped here in the last video. Just a minute. Okay. So here we said that we saw the equation of the RTD. We said that it's R equal to R01 plus alpha t minus T0 plus beta t minus T1 squared and so on. So R0 is the reference resistance, which is measured at T0. So these two variables are related together. They are the reference. After that, we saw that this is the relative resistance R over R0 for different material. For nickel, as you see, it's not a linear curve, but for copper and the platinum, we have a linear curve. So we can use them as a RTD, as material in the RTD. But as you see here, platinum has a more wide range of That means you can measure from minus 200 degrees C up to 800 degrees C. So it has a wide range. So that's why it's the most used in RTD. So the material used in RTD is platinum. If the temperature versus resistance relationship is linear, as we saw in copper and platinum, of a specified temperature range, then approximation of the relationship can be used. So we can approximate if the curve is linear, so we can approximate the equation, the long equation, by this short equation. So it's R0, the resistance R0, R is equal to R0, 1 plus alpha t minus T0, and R0 is the resistance measured for T0. So if we measure the variation of the resistance here, we know alpha, we know T0, it's the reference temperature, so we can find the temperature that we are looking for, where alpha is the material temperature coefficient of resistivity, depends on the material and purity. This is an example of or a table for temperature coefficient of resistivity, which is we said alpha. So here aluminum it's 0.0429, and if we go directly to platinum, which is the most one used, alpha is 0.03927. So here the platinum is the most one used in RTD, and this is its coefficient of resistivity for the platinum. RTD, so platinum is the most common RTD material. This is what we said before. Platinum has a predictable linear over a wide range and reproducible, stable to within 0.005 degrees C electrical resistance to temperature relationship. The final design or choice of RTD measuring device depends on the acceptable level of uncertainty in the final measurement. So if we look for very high precision of temperature, we can use RTD because it's stable at 0.005 degrees C. If we don't need high precision, we can use another type of measurement device. So depending on the application, we have to choose the convenient device for measuring temperature. RTD resistance measurement. So standard ohmmeter, you cause a small current flowing during measurement. So it's based on the current flowing in the system. This current causes the self-heating of the RTD. This loading error may cause a significant temperature change in the sensor. So since we have a current flowing in the wires, so this causes a heating. So the heating will change the resistance in the RTD. So we get an error. We can get error. To minimize the loading error, bridge circuits are used to measure the resistance of RTD. So we use a bridge circuit to eliminate all the external effects on the RTD. The Wheatstone bridge is the most common. So we use in the Wheatstone bridge is the most common used for RTD. So this is the Wheatstone bridge circuit. It is composed by different resistances. We have R2, we have R3, we have the RTD resistance here, and we have a variable resistance R1. And we use a galvanometer to measure the current flowing from in the circuit. This is the ground, or this is the excitation of the circuit. So we have the relationship R1 over R2 is RTD over R3. So R1 is the variable resistance, R2 is this resistance, R3 is this resistance. So R2 and R3 are fixed, and this is the resistance in the RTD. For more detail, refer to page 201 to 205 in chapter 6. So this is the circuit used to use for RTD. We have another, the Wheatstone bridge can be 3-wire or 4-wire circuit. So the Wheatstone bridge does not compensate for the resistance of the lead with its major source of error in RTD. So since we are using wire here, so the wire add the resistance to the system. So this resistance added by the wire can affect the reading of the RTD resistance. So we have to compensate for this resistance in the wire. So for greater accuracy, 3-wire and 4-wire bridge circuit are used. So we have a 4-wire or 3-wire configuration. And lead wire 1, 2, and 3 have resistance R1, R2, and 3. So we have R1, R2, which is the resistance in the wire, R3 is the lead wires. And we have RTD, the resistance of the RTD. We have a variable resistance R3, and we have R1 and R2 are fixed. And we have a galvanometer to measure the current, and we have the excitation here for the circuit. So when we would like to compensate for R1, R2, R3, we can use a 3-wire or 4-wire bridge circuit. So 3-wire Wheatstone bridge circuit. Here we have at balance condition, we have R1, as we see R1 over R2 is equal to R3 over RTD. This is the equation of the resistance of RTD. With the lead wire resistance included, if we include the resistance in the wire, so we get R1 over R2 is R3 plus R1 over RTD plus R3. So as you see here, the R1 and the R3 affect the resistance RTD. If R1 is equal to 2, so if we get R1 equal to R2, that means R1 is equal to R2, then RTD can be found as RTD R3 plus R1 minus R3. So if we put R1 equal to R2, or if we use R1 equal to R2, the resistance in the RTD is given by RTD is R3 plus R1 minus R3. Now if R1 is equal to R3, the effect of this lead is eliminated. So this quantity, if R1 is equal to R3, so this is 0. So we get our RTD is R3. So that's how we can cancel the resistance in the wire. We have to choose R1 equal to R3 and R1 small r1 equal to small r3 and the big R1 equal to big R2. So R2 does not contribute to any error at balanced condition because no current flow through the galvanometer. So since no current is flowing in the galvanometer, so there is no effect of the R2. If we come back to the circuit, the galvanometer is here, there is no current flowing in the galvanometer, so R2 has no effect on the whole system. 4-wire Wheatstone bridge circuit. A 4-wire bridge provides increased compensation for lead wire resistance. So this is a 3-wire configuration, and this is a 4-wire condition: wire 1, wire 2, wire 3, and wire 4. So 4-wire configuration. So here RTD is plus R3 is R3 plus R1, and we said if R1 equal to R3, so we get RTD equal to R3. So if we choose R3 equal to R1, we eliminate the effect of wire. Here RTD plus R1 is R prime on 3 plus R3. So RTD is R3 plus R prime 3 over 2. And also R1 is equal to R3. So we get R3, RTD is R prime 3 plus R3 is the second measurement of R3 divided by 2. Combining the equation on the last slide yields RTD is R3 plus R prime 3 over 2. This eliminates the effect of lead resistance. Note two measurements are required, one for each bridge configuration. So here we need two measurements to find R3 prime and R3 again the same resistance, and we make two measurements to get the value of RTD. So it will be the mean R3 plus R prime 3 over 2. This is how to measure this is RTD. Thermistor. So thermistor, thermally sensitive resistor, typically ceramic-like substance. So it's based on semiconductor. Are semiconductor devices that have a large decrease in resistance as temperature increase. So the relationship between resistance and temperature is generally of the form R, which is the resistance in the wire, is R0 E beta 1 over T minus 1 over T0. So R0 is the resistance measured for T0. So they are known. Beta is known. So when we get the resistance, we can get T. So they are related together. So when we read R, we get directly from this equation T, because R0 and T0 are known, and beta is known. Beta range from 3,500 to 3,500 to 4,600. So this is the range of beta, depending on the material, the construction and the temperature. So when we use a specific material, we get specific beta. So beta is known, and the range of beta is between 3,500 and 4,600. Thermistor resistance. So as you see, this is the resistance of T divided by the resistance of at 25 degrees C, and this is the temperature. So beta here it's 3,395 Kelvin, and here for the second material is 3,900 Kelvin. So be careful here, the temperature are in Kelvin. So when you use the previous equation, T1 and T2 should be in Kelvin. So T1 and T2 in Kelvin. So be careful, we have to convert T1 and T2 in Kelvin, because beta is in Kelvin. Thermistor practical consideration. Value of beta must be considered over a significant range of temperature if measurements are to be accurate. Thermistor provide high sensitivity, so it's high sensitivity, redundancy, and fast response time. It has a fast response time. The high resistance of the thermistor compared to RTD eliminate the problem associated with lead wire resistance compensation. So in the thermistor we have high resistance. So the effect of the lead wire, that's mean the resistance in the wire, doesn't affect the reading of the resistance in thermistor. So we don't need any resistance compensation. Okay, we keep this part, which is about thermocouple, because it's the most used in industry, in the next video, inshallah.